In this video, we're starting off with a point in Cartesian coordinates, and we want to convert that point into polar coordinates. We're also going to make a sketch of the point right from the start so we know if the points that we find at the end of the day are in the right quadrant and match with the original point. All right, so the original point that we're given here in Cartesian coordinates is x is equal to square root of 3. So we're somewhere along the right-hand side of the xy plane because x is positive, and our y value is -1. So we're somewhere on the bottom half of the plane where y is negative. Well, that leads us into quadrant 4. X is positive and y is negative. So again, the way in which we do this is we move out a distance of, say, square root of 3 from the origin, and then we move down a distance of 1. So our point in this problem is this point in Cartesian coordinates of square root of 3 minus 1. So the important thing to take away from this is basically that we are in quadrant 4. That's where the point that we care about actually lives. All right, so that being said, we know where the polar points should take us at the end of the day, at least in what quadrant. That information will be coming in handy in a little bit. Otherwise, how we make moves from here is we want to use our polar coordinate Cartesian coordinate transformation equations, or how we can convert back and forth between coordinate systems, going from x and y to r and theta, or r and theta back to x and y. In this case, we're trying to get the r and theta values, the polar coordinate representations, when we're starting with values in x and y, or Cartesian coordinate representations. Now, just as a spoiler, we're going to see in a moment that there's actually two different polar coordinate representations for one point in Cartesian coordinates. So where to go from here? Let's see what those transformation equations look like. So again, we're asking which ones do we use and when? Well, in this case, we're starting off with point in x and y coordinates. So we want to take that x and y information and get r and theta. So that would suggest using the transformation equations on the left side, where we can get r from x and y, and we can get theta from x and y as well. So let's start doing that. Let's start doing those. Finding the polar radius first, let's say. So we have r squared is equal to x squared plus y squared. And now we're going to substitute the information that we're given into the problem. We're told that x is equal to square root of 3. So we have r squared is equal to, substituting square root of 3 in for x, we have square root of 3 quantity squared. Now substituting in the -1 for y, we have plus -1 squared. So we find that r squared is equal to square root of 3 squared, which is 3, plus -1 squared is a +1. So r squared is equal to 4. And now when we take the square root of both sides, we have that r is equal to, and this is important, plus or minus the square root of 4. So we find r is equal to plus or minus 2. And again, I'm trying to emphasize here, we have plus or minus 2. So we really have two r values. We have r is +2, and we also have r is -2. So a moment ago, when I said there's going to be two different polar coordinate representations, you can see, well, we already have two different polar radii to work with. And as we'll see in a moment, we're also going to get two different angles to work with as well. All right, so let's work on that angle, speaking of. So the other equation we have is the tangent of thetas equal to y over x. So we'll do the same thing, plug in the values of y and x. So in this case, again, y is equal to -1. And x in this case is equal to square root of 3. So we have the tangent of theta is equal to -1 over the square root of 3. So again, what we're looking for here is the theta value whose tangent is equal to -1 over the square root of 3. Another way we can say this using inverse trig is we have theta is equal to the arctangent of -1 over the square root of 3. So we're asking the angle whose tangent is equal to -1 over the square root of 3. So let's just remember some things about unit circles and the angles of those unit circles for sine, cosine, and tangent. So our unit circle angles, things like 0, pi over 6, pi over 4, pi over 3, pi over 2, and we can think about those different angles in different quadrants of the xy plane. Now, what we're told in this case is we have a negative 1 over the square root of 3. The reason why I'm pointing that out is negative 1 over square root of 3 is what we actually see is tangent is a negative number. And tangent is negative in either quadrant 2 or in quadrant 4. So we're looking for angles, basically, whose sine and cosine have opposite signs. And well, in this case, if we're looking at the connection, the angle in the first quadrant, who has a tangent related to 1 over square root of 3, that is the angle of pi over 6. So we're basically looking for the angle of pi over 6 in quadrant 2 and in quadrant 4. So let's think about those real quickly. So if we're thinking about those angles, the first angle in quadrant 2, well, that's going to be the angle in which we have theta is equal to 5 pi over 6. So one of the angles that we have to work with is theta is 5 pi over 6. Now the other angle we have, we can think about it either two ways. We can either add pi basically to 5 pi over 6, or we could just start off with the positive x-axis and subtract the angle of pi over 6. So the next angle, either way, is going to circle us all the way from the positive x-axis into quadrant 4, which if we loop this around, will basically give us this angle, of either theta being equal to 5 pi over 6 plus pi, which is equal to 11 pi over 6, or equivalently, we could have just started from the positive x-axis and then subtracted off pi over 6 and have theta is negative pi over 6. So either of those two will work. Let's just, for the time being, let's just use our 11 pi over 6 here. Both those angles, 11 pi over 6 or negative pi over 6, that would have placed us in the quadrant 4 that we care about. So at this junction, what we have is we have two different polar radii, and we have two different possible angles. So the name of the game now is which radii goes with which angle, and vice versa. Okay. So let's start off with the first thing I do, which is basically, let's think about a positive polar radii at first. Because what a positive polar radii tells us is, we're going to move a distance equal to 2 now from the origin. And since that polar radii is positive, we're going to move that distance 2 in the direction of the angle it's paired with. So in this case, if we have r is 2, we want to be in quadrant 4. Let's take this 11 pi over 6 angle. Because if r is 2 and theta is 11 pi over 6, what that really means is, again, we're going to move at an angle 11 pi over 6. That places us in quadrant 4, and we move out a distance of 2. So it looks like doing those two combinations will place us at the right point. So one of the polar coordinate representations then is 2 and 11 pi over 6. So that is one of those polar coordinate representations. Now there's another one. And well, we already used two of those, one of the radii and one of the angles. So let's just make sure the other one works. So what happens when r is negative 2 and theta is, well, 5 pi over 6? So if theta is 5 pi over 6, that's going to place us in quadrant 2. However, instead of r being positive and moving out in that direction like we normally would, r is actually negative. So instead of moving out in that direction, since r is negative, we actually move in the opposite angle. or the opposite direction at a distance of 2, like we've discussed before. So in this case, this is our point now, 2, 5 pi over 6. Remember, when we have a negative polar angle, we basically add pi to the original angle and then think about the absolute value of the r variable. Or you can just imagine we flip across the origin into the opposite quadrant. So in that case, it looks like this combination of r minus 2 and theta 5 pi over 6, that also lands us in quadrant 4 at the right point. So the other polar coordinate representation is minus 2 and a 5 pi all over 6. So any point in Cartesian coordinates has multiple representations in polar coordinates.